Now let's talk about the magnetic field produced due to an electric current. So Ørsted in 1820 did an experiment. He placed a bunch of compasses around long straight wires carrying current. And what he found was that these compass needles align such that they are all tangent to a circle drawn around the wire. So Ørsted experiment results were the direction of the compass needle is always perpendicular to the direction of the current in the wire. And Ørsted's discovery first provided the link between electricity and magnetism. Then in 1876, first direct experimental evidence for magnetic field of a moving charge was given by Rowland's experiment. What he did was he prepared a disk of charge by connecting a battery to the layer of gold deposited on the surface of a disk of insulating material and rotated the disk about its axis to produce moving charges. These moving charges on gold surface of the rotating disk produced a magnetic field that deflected the compass needles. So in practice, the deflection was very small and it required an apparatus far more sensitive than a compass needle to detect. So these were two experiments that proved that moving charges produce magnetic fields. So what are some of these properties of these moving charges? The field strength of this produced magnetic field is directly proportional to the magnitude of the velocity and also directly proportional to the charge that's moving. If the direction of the velocity is changed or the charge changes sign, the direction of magnetic field produced will be reversed. The field is zero at points along the direction of velocity vector, forward as well as backward. So basically what it's saying is that in the direction that the charges are moving, the produced magnetic field will have absolutely no components. It is only around it. Now the way to remember that, and the other properties are B is always tangent to circles round about V in planes perpendicular to V, and the direction of B is always determined by the right-hand rule. So the simplest way of defining B that is consistent with observation is given here. Q, movement this way, B goes that way, so the direction of B is proportional to Q, V, sine theta divided by r squared, where r is a vector that you determine where, that basically you are at, that you want to find B at. So expressing the above equation, we know B will equals K, which is any proportionality constant, QV times r hat over r squared, or it can also be expressed as mu naught over 4 pi k qv times r over r cubed. This is just another way of expressing it, but for more practical reasons for this particular class, I would like you to remember this value where k is given by mu naught over 4 pi with numerical value of 10 to the minus 7 Tesla meters per amperes. This is the formula I would like you to remember for the magnitude of the magnetic field for a moving charge. B equals mu naught over 4 pi qv sine of phi divided by r squared, where phi is the angle between V and r. The right-hand rule. So remember we were talking about the fact that moving charges will create magnetic fields around it. Now how do we find the direction? We will use another rule which is called the right-hand rule, and what that right-hand rule says that if you hold the current carrying conductor in your hand and your thumb points along the direction of the current, your coiled fingers will give you the direction of the magnetic field. Okay, so like this is the charge conductor and my real current, conventional current, is moving upwards, then this will be the direction of the B field. However, if the current goes downwards, the conventional current goes downwards, then this will be the direction of the B field. A long straight wire segment will actually be, the B field can be calculated by mu naught I over 2 pi d. It can be easily shown by calculus, by using calculus, that B actually is equals to mu naught I over 2 pi d, where d is the distance between your current carrying wire and your point P. P is where you want to find the B field. at. Luckily for us, we will not be required to do the calculus in this particular class. So now let's do an example. In household wiring, two long battery wires are separated and surrounded by an insulator. Wires are kept a distance d apart and carry currents of magnitude I in opposite direction. Find the magnetic field at a distance r, which is much, much greater than d from the center of the wires. Find the numerical value of B if I equals 5, D equals 5 millimeters, and R equals 1 meters. And compare it with the Earth's magnetic field strength, which is approximately 5 times 10 to the minus 4 Tesla. In this question, what we are given are two wires which are separated by a certain distance, D, and we have to find at point P the magnetic field due to these. I will assume that one of them, the top one, in my picture is the one that's going into the page, and the bottom one is the one that's, the top one is coming out of the page and the bottom one is going into the page. Okay? Now my right hand rule, I can tell that this, if I take my finger and I bring it out, my thumb, bring it out, this will give me the direction of the B field. So the B field due to wire 1 is going to be directed that way. This is the current that's going into the page, so the B field is going to have a direction like this. So my B2 field will look like this. Now what about if I was to draw a vector all the way here? So this is my P, so I'm going to get rid of it. It's going to get complicated. Okay? What I know is that this is the R that I want to use. However, if this is D over 2 and this is D over 2, this is R, and if R is much, much greater than D, I can almost approximate both of those to be R's as well. My job is to find the magnetic field at point P. Now how do I find the magnetic field at point P? It will be a sum sigma B net will be B1 plus B2. Now, again, remember, this is going to be a vector, so it's going to have vector components, which will be B1x I plus B1yj plus B2xi plus B2yj. And I can assume, I can choose my coordinate system any way I want, so I can choose this to be x and this to be y. Okay? Now how does this go? So the direction of B is these and these. What will it look like if I was to take one of these charges? So I'm going to choose this color. Okay? So if I was to take this charge and draw the field according to this charge at this point, it will look like this. Why? Because if I just look at this, watch what happens. That's what the B field is going to look like. Yes? So the direction of the B field, according to B1, will be this one. What about B2? Well, this goes here, right? So that basically means is by the time I come here, it should look like this. So every little vector, it will point like that. So at this particular point, B2 will look like that. Okay? Now I have to find its components along the x and along the y. So B2, this will be B2 sine theta. This will be B2 cosine theta. Okay? And this will be B1 cosine theta. This will be B1 sine theta. Okay? Now watch very carefully. What happened? This is B1 cosine theta. This is B2 cosine theta. They are exactly equal and opposite to one another. Hence, they will cancel out. But we will get B1 sine theta because B1 sine theta also points this way and B2 sine theta also points that way. Okay, so what we are going to end up with is this only being 2b sine theta. Okay? Why? Because b1 sine theta and b2 sine theta, b's are equal and opposite, right? So b will remain the same and I get this. So sigma b net will not be nothing other than 2b sine theta. Okay, now how do I find b? B will be mu naught I over 2 pi r, right? And sine of theta, this is theta, and this is theta. So sine of theta will be d over 2 over r, because it is perpendicular over hypotenuse. Okay? If I plug those values in here, my b will be mu naught I over 2 pi r. Sine theta will be d over 2 divided by r. I simplify it and I get mu naught id over 2 pi r squared. For my B field for two current carrying wires at any point P much further away than D. Another thing that we will talk about but will not derive is called the circular current loop. So a B field due to a circular current loop, which is also an application of Biot-Savart law, is given by mu naught I over 2 pi r. There is a whole derivation in calculus that tells you how it is derived and everything, but for you, all you need to do is remember what this formula is. So a solenoid is a way of forming a uniform magnetic field. Okay? Solenoid is just a helical winding on a cylindrical core. The wires carry a current I and are wound tightly together, so there are n windings per unit length of a solenoid. So inside the solenoid, the magnetic field is going to be completely straight. For an ideal solid, the length is much, much greater than r, and in this case, B will be equals to mu naught Ni, where N is the number of windings and I is the current that flows through it. Magnetic fields of an ideal solenoid and two non-ideal solenoid as a function of distance from the center are given below. So for an ideal solid, basically what you have is inside, it is completely constant, the B field, and outside it goes to completely zero. However, in real life, the fields kind of look like this. But in general, if you make solenoids big enough, you can ignore the edge effects on the outside. This is what the magnetic field will sort of look like. So on the inside, the fields will be completely straight. So the limiting case of an ideal solenoid is interior points fields become uniform and parallel to the axis. On the exterior points, field outside the solenoids are completely zero. Where are these used? The biggest example where these phenomena are used are in magnetic resonance imaging.